Space is a vast and unforgiving environment. Rockets, those magnificent feats of engineering, must navigate this emptiness with precision. Imagine a ballerina gracefully pirouetting across a stage. A rocket, too, performs a delicate dance, but its stage is the cosmic void. This dance is essential for the rocket to point its instruments, communicate with Earth, and ultimately reach its destination. But this cosmic ballet is no easy feat. Unlike a ballerina who can feel the stage beneath her feet, a rocket has no such reference point. The vacuum of space offers no resistance, no up or down, no sense of direction. How then does a rocket maintain its balance and orientation in this ethereal realm? How does it keep from tumbling head over heels like a discarded toy? The answer lies in a fascinating blend of physics and engineering. Rockets employ a variety of techniques to stabilize themselves, ensuring they stay on course and fulfill their missions. Join me now as we delve into the intricacies of rocket stabilization, a testament to human ingenuity and our relentless pursuit of the cosmos. Imagine a sailboat catching the wind, its sail billowing as it glides across the water. In space, however, there is no wind, no air to resist motion. Yet, even in this vacuum, rockets face unseen forces that can disrupt their delicate balance. One such force arises from the rockets themselves. Thrusters, those powerful engines that propel a rocket through space, can sometimes fire unevenly. Imagine a garden hose with a kink in it. The water sprays out at an odd angle. Similarly, a misaligned thruster can nudge a rocket off course, sending it into a slow spin. Gravity, too, plays a role, though not in the way we might expect. The Earth's gravitational pull weakens with distance. This means that the bottom of a rocket, being slightly closer to Earth, experiences a slightly stronger pull than the top. This difference in gravity, known as gravity gradient, can cause a rocket to drift out of alignment. Even sunlight exerts a force, albeit a tiny one. Imagine a beach ball on a windy day, being pushed around by the air. Similarly, photons of light from the sun can nudge a rocket, especially if it has large reflective surfaces. These forces, though subtle, can accumulate over time, jeopardizing a mission's success. To combat these unseen forces and maintain their stability, rockets employ a suite of ingenious technologies. One such technology is the gyroscope, a marvel of engineering that has been guiding us for over a century. Imagine a spinning top, stubbornly resisting any attempt to tip it over. A gyroscope works on a similar principle. It consists of a spinning wheel mounted on a set of gimbals, allowing it to rotate freely in any direction. As the gyroscope spins, it develops a property called rigidity in space, meaning it resists changes to its orientation. By sensing any deviations from the desired orientation, the gyroscope sends signals to the rocket's control system, which can then fire thrusters or adjust the spacecraft's orientation. Another crucial technology is the reaction wheel. Imagine a bicycle wheel, spinning freely. When you try to tilt the wheel, you feel a force pushing back, resisting your attempt. This force is due to the conservation of angular momentum. A reaction wheel, essentially a heavy wheel mounted on a motor, utilizes this principle to control a rocket's orientation. By speeding up or slowing down the wheel's rotation, engineers can transfer angular momentum to the rocket, causing it to turn in the opposite direction. This method is incredibly precise, allowing for minute adjustments to the rocket's orientation. Imagine a figure skater, gracefully spinning on the ice. As she pulls her arms in, her spin accelerates. This phenomenon is due to the conservation of angular momentum. Angular momentum is a measure of an object's tendency to keep rotating. Just like linear momentum, which describes an object's tendency to keep moving in a straight line, angular momentum is a conserved quantity. This means that in a closed system, with no external forces acting on it, the total angular momentum remains constant. A rocket in space, far from any planets or stars, can be considered a closed system. Therefore, its total angular momentum must remain constant. This principle is fundamental to understanding how rockets maintain their orientation. When a rocket wants to turn, it doesn't simply push off against something, like a car turning its wheels on the road. Instead, it utilizes the conservation of angular momentum. By changing the angular momentum of internal components like reaction wheels, the rocket can rotate in the opposite direction, keeping its total angular momentum constant.